My name is Dheeraj. I'm a senior staff CAD engineer at Qualcomm. And this is my colleague Nicholas. He's a senior engineer at Qualcomm. And, we are essentially flow methodology engineers at Qualcomm. And, our expertise is to build and automate workflows in the chip design space. Right. So I'm hoping that this talk, essentially covers, two areas. One is to showcase our use case for our Airflow community here, and the other aspect of it is to show the semiconductor industry that Airflow is really a very good solution to orchestrate their workflows. I know a lot of my colleagues spend a lot of hours developing custom workflow orchestrators, which essentially can all be deprecated because Airflow is a really good solution. So I'm hoping this to be the start of Airflow in the semiconductor industry. So and let's just take it from here. So I'm gonna just skip through the agenda because we have a lot of material to cover. Let's just talk about who we are. We are the Qualcomm Oryon CPU team within Qualcomm, and our CPU is the CPU that goes into the Snapdragon lineup of chips. So, if you happen to have, a latest Android smartphone, chances are you're using our CPU in there. So, and Airflow has played a critical part in the design process of the chip, right? So, and we also have mobile and automobile offerings as well. So, do check us out. With regards to the nature of workflows that we run, our typical task essentially runs an EDA workload. So I have the definition of what EDA workload is, but essentially, these are compute-heavy, workloads. Like, for example, a typical EDA simulation, it's not uncommon for it to ask for, let's say, 8 to 16 cores of CPU, 256 GB of RAM, and then generate, hundreds of GBs of, log files and IO. So these are pretty heavy, workloads. Apart from that, these workloads, is not just one or two tasks that we run. We run millions of tasks every single day, right? So we are very, very, very compute, hungry, and our workloads run across multiple data centers spread across many different geolocations. So that is the nature of problem that we are currently dealing with. And the problem with these workloads is that they can't really be run in Docker, right? So but the problem with Docker is Docker needs root privileges, for the most part, you could say, but that is definitely a no. There's no native scheduler integration, and I'm going to talk about that a little bit in our next slide, where we use specific HPC schedulers like Slurm or LSF, which gives us access to specific resources. So I could just say my job takes 4 CPUs, 16 GB of RAM. I can't really do resource allocation in Docker. Right. The other problem that we have is, file system overlay. So EDA tools, basically need access to millions of small design libraries. And then, these are mounted across, hundreds of mounts in our file system. So it's not practical to mount everything in a Docker container and have that read in. So that's going to be a very slow process. And then the plethora of other reasons why, Docker is not the way to go for us, right? So what the industry uses is, we use LSF and Slurm for, our job scheduling, and we use Singularity containers, which work very well with HPC. So this is an industry standard practice. So it's not unique to us. But the advantages are that the Singularity containers they don't run as root, they run as the user who triggered the job. They also have native resource tracking and fair share allocation, right? Also, it has direct access to the file, the native file system. It doesn't have to be mounted, and it also inherits the host limit. So this is how most of our workloads basically run in our compute farm. right? So this is an overview about how, what is the nature of our workload. So I'll just hand it over to my colleague here to talk about what life was before, we had Airflow in.
Yeah, so I'm going to talk about life before Airflow. I'm going to start with a quote here. Before there was automation, before there was orchestration, there was chaos. And before there was chaos, there was Jenkins. So what's wrong with Jenkins? Many of you who have experienced it before know it to be pretty unstable. Executor host nodes are going down constantly. A lot of different failure modes leading to this. Overall, the infrastructure of Jenkins is fairly brittle. There's a lot of maintenance overhead to keep things running smoothly. A lot of manual deployments. Generally, bad experience. Another, aggravating factor in our situation was that we were relying very heavily on unversioned, not checked in, freestyle workflows that were hard to generalize across teams. Pretty much never maintained, except by the engineer who set them up. And very difficult, to scale and maintain the quality of. So a lot of jobs were breaking all the time. And, we needed something better. So what's good about Jenkins? Well, you can throw a shell script in there and press play. Pretty much works all the time, except when it doesn't. Some people see that as a flaw. And now, Jenkins is holding us back. Okay, we needed something better. We needed a serious upgrade. And we found it with Airflow. And Airflow offered us scalable, stable, and automated pipelines that we could write in Python, that we could properly review, check into a repository. And really critical for us is that it offered a very usable, visually organized web interface that offered a lot of technical depth, auditability, and logging information that engineers could use, to evaluate the workloads, as well as present information to less technical people, analysts, and program managers throughout the organization. So now we're going to talk about the production instance we use at Qualcomm, and how we deploy things, what we had to work through to get there. So, Dheeraj?
Yep. Thanks, Nick, for that. So this is what we started out with, during the when we moved to Airflow 2.10, 2.8 or something initially. So all of our Airflow core services are on a virtual machine and are hosted in a Docker container. And all of our workers are Celery workers, which share the Airflow install, which is installed on NFS. So this is what we started out with. So the main problem that we had with Jenkins is that we had hundreds of nodes, and we did not want to manage all of those nodes that were that we had up there. So we really wanted like a simple solution where we could leverage our LSF Slurm job scheduler to basically spin up Celery workers on demand. So that's essentially what we came up with. So this is what we call dynamic Celery workers, where in our data center, we just have one Celery worker, which is always active, which we personally maintain the health of. Every other Celery worker is dynamically launched through our NSF job scheduler. So you can look at some of the job, how it looks like. I can say job, CPU is 8 and then 64 GB of RAM, and then launch Celery worker. And then I have a Celery worker that pops up in our compute farm. So I have a sea of workers. So I have a DAG that automatically launches Celery workers on demand. And because this is a Slurm job, essentially they have, it has a wall time. So these workers are short-lived, right? So I have, the least time of these workers baked into the name of the worker. So I have a DAG that periodically checks to see if the least time is expired. And if it is, it, automatically decommissions it. So, and then brings it down. So the workers are always, circulated basically. And, generally the health is screened. So to get all of this working, right? So Celery did not have a way to be able to, the Airflow command line, I would say, did not have a method to, shut down a worker remotely. So that's what we've contributed, on the Celery front, where we extended the CLI to be able to remotely manage the queues and shut down the Celery Workers. So this is what we've done in the last year. So now, we have an elegant solution. People started out using Airflow, and then, but teams are pretty happy. Teams are, getting onboarded, and, now we are posed with a problem where, to give us an example of scale, we run, 1 to 2 million simulations every day, right? And at any given point of time, we are using 500,000 to 800K CPUs at any given moment in time. So we cannot, our compute needs are beyond a single data center, right? So as more and more projects essentially come in, we needed a solution where we need to route our jobs to wherever compute was available. Qualcomm has, multiple data centers spread across, globally, and, we have some cloud access as well. So, as and when we have capacity in these different areas, we want to route our jobs to these different locations. That's problem number one. Challenge number two is once our design is complete and then we tape out our chip and then we get the chip back from the fab, we needed a way to launch, the same test that we have done on our, pre-silicon phase to be done in the post-silicon phase. We want to run the same test on the custom silicon boards that basically come in. And these are essentially hooked up to certain hosts which are in our lab. So the question is, can Airflow basically do all of this, right? So this is when I was in last year's Airflow Summit and I stumbled upon Jens, who, he connected, bit, and then, that's when I found out about the EdgeExecutor. Worked with him over the last year to test the, 1.0 version up, and then glad to say that, today we are on Airflow 3.1 with Celery and Edge completely, functional across multiple data centers, right? So the idea is straightforward, where similar to Celery, where we have one, permanent worker and then, multiple, short-lived workers. The edge is also the same, where we have one edge worker in every data center that we have, which is always alive. And the only responsibility of the edge worker is to spawn more edge workers, which actually, do our task, right? And, no more, data center handcuffs. We can route our jobs to any data center based on, the capacity. So when I see, data center A has, 50,000 CPUs available, I want to be able to change the queue of the edge worker, and then boom, all of my workload is moved on to, data center A, right? So that's truly what we've been able to achieve. And, the other thing is we've been able to install Airflow on the hosts that are connected to our custom silicon boards. So, we've been able to use the same Airflow instance to be able to launch, tests to run on custom silicon, using the edge worker. So it's, truly distributed. So, this is a good example. So this is what it actually looks like in the lab, where, we have our custom silicon that's sitting there, and then we have the virtual machine or the machine where, the edge worker is running. So, and this is, basically our Airflow 3.1 architecture that we have in production today, where, local jobs are on Celery, remote jobs are on Edge, and, basically I could use Edge for the local, jobs as well. There's nothing holding us back, but, we truly orchestrate jobs across multiple clusters. So at this point, I'm going to hand it over. Oh, I forgot about that. So in order to get all of this working, right, so we needed to make, several enhancements to, Celery and Edge. So these are all of the enhancements that we have been able to contribute back to Edge and Celery. And then, apart from that, we made a bunch of other contributions as well. So if you're interested, you can scan the QR code. Okay, I'm going to hand it over.
Thanks, Raj. So I'm going to try and run through some actual examples of methodologies we use in our production instance. And there's a lot of slides here, so I won't be able to really dig into all of them as much as I want. But we're going to start with just like a generic kind of boilerplate example of the type of workflow we use at Qualcomm to just, get basic work done. Okay, so here's an example of a DV, design verification, Workflow, okay, we're going to create a run directory, make sure there's enough space in the scratch disk, check out a design from a given version control software, and then run a series of EDA tools on top of it. You see here, generate design file list. A file list in the context of EDA tools is a list of hardware modules that are sensitivities to your piece of hardware that you're designing. Generally, a file list is ingested by a simulator to compile your design, make sure it elaborates and synthesizes cleanly, and then actually run the simulation. Work your design through different pieces of behavioral context, and qualify the results to see if your design actually works. If you look on the power team, you might do something a little different. Okay, you run the simulation, but on top of that, you generate waveforms. Okay, which you can just think of as a time series graphical value of every single signal in your design. All right, we have big chips. We have a lot of different layers to it. So this is a ton of information that may get dumped into a waveform output. And the way the power team might actually use this information is make some inferences and use the actual time series signal values of different pieces of your silicon design to estimate power usage in in different operational scenarios. This is really critical information for designing a chip. Okay, you need to make sure your design is running within a given power budget, and you're actually able to claim that our chips are actually really efficient. Another example for the physical design team. Okay, they're responsible for taking your actual designs and fitting them into rectangles on a piece of silicon. So they might use something a little different. Okay, they might just take file list. Okay, and try and attempt to fit each piece of the module into a given piece of silicon. Okay, the way they can do this is by taking some a priori assumptions about how big a given module is going to take on a given tech node and a given piece of silicon, and use that information to ensure that the entire design can fit into the allotted space. Again, so this was my kind of passion project for Airflow, and it is where the bulk of my effort went into while we were transitioning to Airflow 3. Okay, many DAG developers here may be familiar with the relative lack of a comprehensive unit testing framework in Airflow. That was a constant kind of barrier to testing different pieces of our code base. And we like dag.test that exists is incredibly helpful. It helps us verify very complicated DAGs locally, which is a must, right, for local development, as well as the DAGs list import errors command in Airflow 2. That was the primary smoke gate to our code base before we adopted Airflow 3 and before I put this little plugin together. So anyone who has contributed to Airflow before may be familiar with the Breeze tool. Long story short, I ripped that thing apart and I put it in our code base. And now we are running our smoke checks as well as, pretty complicated unit tests across the board in our code base. So on the right, unfortunately, it's pretty hard to read. That says test integrity. Okay, this is our drop-in replacement. I have a Python unit test, a PyTest unit test, to do the list import errors function. Okay, so it loads the DAG bag, it disables reading from the DB, throws away the examples, and checks if there's any import errors present in your DAG bag. And what we also do is we evaluate some of the DAG bag stats that are present along with the DAG within the DAG bag to like fail a PR if a given DAG is taking too long to process, basically. So this function here, it's gonna block check-ins of bad DAGs. Another example on the left side is an actual example of a fully self-contained test DAG that for example might have a couple building blocks of our generic workflow template within it. This plugin doesn't actually spin up like a scheduler or a trigger or anything like that. So we just manually create a diagram beneath, get the task instances, run them in order, make sure that the states evaluate to true or whatever you would expect it to. And, this lets us pretty much test a full DAG, locally. It's not DAGs.test, but it's something like that. Now on the right side, this is a stripped out unit test from Breeze for the bash operator that we use to test our own custom shell operators. So working in the semiconductor industry means that you have to use very old shells and very old, RC profiles to execute like anything pretty much. It's pretty old. So we had to, customize the bash operator. We had to make an operator for the tcshrc shell. I don't know if anyone's ever heard that. That's a big hardware type of shell, as well as a custom subprocess hook to allow us to move a lot of post-processing for certain shell tasks to post-execute hook. We use this all over the place to, in both the pre and post-execute hooks, to do a lot of different things. Specifically, we do a lot of log scraping, log parsing, trying to get the certain variables into XCOM outputs that we can use in some meaningful way within our DAGs, as well as like smart retries, which we use for the OSIF grid to intelligently retry a operator. For example, we're having like grid issues, grid contention, or failures to submit a job. Finally, we also use DAG templates. We have our own kind of version of DAG factories that Dheeraj said. When we first were building out the Airflow instance, and I guess the main difference here is that since we have so many DAGs organized by project, by team, by maybe submodule within the chip design, we wanted to organize like hierarchically all the different DAGs in our code base. Okay, so what this looks like is we still have a YAML configuration file that primarily defines the like DAG runtime params and other like characteristics of the given DAG, maybe the project specific, maybe they have different runtime constraints, different knobs, whatever. So we use the YAML files along with predefined DAG templates. Okay, users will create a symlink, points to the DAG template, they'll set up a YAML dictionary to configure it, and that is how the actual DAGs are kind of stamped out by team. That's how we get designers to bring up DAGs without writing any actual code. This works for us. Obviously creating a symlink is, it's a thing you have to do, but we do have a unit test that, kind of enforces this methodology. That is the talk.